Hello, ladies and gentlemen. This is Mr. Hunter, and this is part two of your projectile notes. So right now I'm going to tackle the second example, and I'll probably call it there because I don't really want to start the third example. The third example is pretty lengthy. So in example number two, we have a ball is thrown off the edge of a cliff, which I just noticed now that the text is wrong. I will change that in the future. But anyways, a ball is thrown horizontally off the edge of a 50-meter high cliff with an initial velocity of 20 meters per second. This is very similar to the do now that I gave you this morning. So in physics, it is often very helpful to go ahead and draw a picture of what's going on. So in this case, I have a 50-meter high cliff, and I have a ball being thrown horizontally off of the edge at a velocity of 20 meters per second. Now, it's very important to note here at this point, hopefully you're getting used to starting to write some of the things that I say because they're really useful. For example, X's and Y's are like, and you'll finish that statement, Bloods and Crips, they don't mix. I know it's a crude example, but you don't use X's together with Y's and vice versa. They have to be totally separate and independent, which is the next skill that I want to teach you. The next skill that I want to teach you is the T-chart. Because X's and Y's are so totally different in here, we still use the same equations that we've been using before, but we only apply them to the X and Y variables separately. So for example, in the X, we can now list what we know and what we know in the X and what we know in the Y. So let's list our variables. It says a ball is thrown horizontally off the edge of a 50-meter high cliff. So they just told us that our distance in the Y equals 50 meters. Notice what I stated before as well is that now I'm writing the variables with the subletter of Y or X so that you know, okay, this is the x-axis and this is the y-axis. You should be doing this too when you write down variables so you don't mix them up. Because if you don't, you will mix them up. So make sure you write dy or viy or vix, so on and so forth. So right now, we don't know the distance in the x. That is a question mark. That's something we're going to figure out. So let's go to the next thing. The next thing they seem to give us is velocity. They say it's thrown horizontally off the edge of a 50-meter high cliff at a velocity of 20 meters per second. When they throw something horizontally, that is your keyword clue that your initial velocity in the y direction is 0 meters per second, which means that the velocity that they gave is in the x direction because that's horizontally, so that is 20 meters per second. So now we have to figure out other things that we know or don't know. So one thing we can eventually figure out is VFY. That's a question mark. We don't know that. We also know one more piece of information. And the piece of information that we know is the acceleration in the y direction. Actually, excuse me, there's two more pieces that we know. The first being that acceleration in the y is 9.8 meters per second squared. Now, because the object is only going down, I'm going to say, hey, you know what? The down direction into the right is positive because those are the only directions we're going, so let's make our math easy for ourselves. Now, here's the thing. We are ignoring air friction, and because we're ignoring air friction, there's no force to cause an acceleration. Remember in the previous gravity notes, force causes an acceleration. Because on the x-axis there's no force, I could say that my acceleration on the x-axis is 0 meters per second squared because I have no acceleration. And if that's the case, if I have absolutely no acceleration, and acceleration being the definition of change in velocity, which is all review, guys, then I know that my final velocity in the x also has to be 20 meters per second because it doesn't change. Because the acceleration in the x-axis is 0. So the only thing we really need to figure out on the x-axis so far is our distance in the x, which is probably the last step we'll do. Lastly, ladies and gentlemen, and this is critical, that's why I put a star next to this. Even though time is the same for both x and y, you use y to find time because the acceleration on the y-axis, your initial velocity on the y-axis, is the only thing that dictates how long it takes to get to the ground. So we figure out time using the y variables. So just like today, when I asked you to find the time it takes, we can only use the y variables. So we have VIY, dy, a of y, and time. And so you look at the equation to say, okay, what is the only equation that uses those variables? And that's diy equals VIY times time plus ay t squared divided by 2. And when I do that, I can just now plug in. So my distance in the y was 50 equals initial velocity of time is 0 plus 9.8 times time squared divided by 2. So this is actually the exact same number in your do now from this morning. So t squared, then I divide out the 4.9, divide out the 4.9, and I get t squared equals the square root of approximately 10. And so I get t equals 3.2 seconds. So I now found the time that it takes to hit the ground. So remember, time is solved by the y variables, but it still applies to the x. It's the total time in the air. So my time equals 3.2 seconds. So the only thing I need to figure out 2 more variables, and we're done with this example. I need to figure out my final velocity in the y and my and my distance in the x. So let's figure out the VFY. We have plenty of variables to choose from. We have time, we have initial velocity, we have final velocity, we have the distance, and we have acceleration. So we can choose any equation we want to solve this. So I know you guys have room on the back, so flip to the back, and instead of being example 1, because I didn't use that room at all, just let's put example 2 room. So since this is example 2 room, let's see what we had. So we had our distance in the y equals 50 meters. We had our acceleration in the y equal to, come on, Mr. Hunter, 9.8 meters per second squared. And we had our VIY equals 0 meters per second, and we want VFY equals question mark. So therefore, I'll use VF squared equals VI squared plus 2 times acceleration times distance. And I'm just going to solve for VF. Oops. Notice I did not put my y's. My bad. Okay, now my y's are in there, so I get VF y squared equals 0 plus 2 times 9.8 times 50. 50 times 2 is 100. So then we have 100 times 9.8, which is going to be, what, 980. So then I'm going to get VF squared and the y equals 980. And then I square root both sides to get rid of the square. So the square root of 980 is going to be 31.3. So the final velocity in the y direction is 31.3 meters per second. So that's the final velocity in the y direction. So we can go plug that back in. But if you notice, all I'm doing is now using LEPA, but we're being meticulous and using the x and y axis. So we're going to have to do this last example on the side right here. So now we need to find distance in the x, right? Well, we know the acceleration in the x equals 0. And we know that our initial velocity in the x equals 20 meters per second. And we know it takes a time of 3.2 seconds to get to the ground. So if I use d equals VIX plus AX t squared over 2, Now, this side goes away, and I apologize for running out of room. So try to fit this in your notes or just try to fit it in the sidebar somewhere and just write smaller. So because acceleration is 0, this whole side goes away because it's 0. So all I'm left with is d of x, dmx. Anyways, d of x equals vix times time. So the distance in the x is literally just 20 times 3.2, which equals what? 60.4, right? Am I doing my math in my head right? 3.2 times 60, or 20. 3.2 times 20. 3.2 64, excuse me, not 60.4. So the distance in the x is 64 meters. So it goes 64 meters from the edge of that cliff. So just from having two solid pieces of information, you were able to actually figure out how far it landed from the edge of the cliff. We were able to figure out how long it takes to get to the bottom. We were even able to figure out its final velocity at the bottom just before it hits the ground. So I'll be looking at these notes Tuesday, and we'll also be practicing some examples in class. See you then. Bye.